In this video, we're going to talk about a type of problem called a related rates problem. Sometimes we are required to figure out the rate at which something is changing when we are given the rate at which a related quantity is changing. For instance, if we know the rate at which the sides of a square are growing, we may be asked to find the area, the rate at which the area is growing. In fact, we'll do an example like that. So this technique requires us to use something very similar to implicit differentiation. We're going to be differentiating with respect to t, and so we'll do an example. In fact, let's do an example right now. Alright, so let's look at this example. It's not a very interesting example, and it's not one that is particularly useful, except that it'll illustrate some of the mechanics involved in figuring out a related rates problem. So let's say you've got y and x related by the equation y equals 1 over x. And x is growing by 1/2 unit per second. So if you imagine, say, the graph of 1 over x, you're asked how fast is y changing when x equals 10. So let's say we're going way out here at x equals 10. And now x is changing by 1/2 per second. So it's increasing by a rate of 1/2 per second. So that tells us something about how fast we're going here. Now, as x increases, the y is going to decrease. And so the question is, how fast is y decreasing at that point? All right. So this is a rate. It's a rate of change. X is growing by 1/2 unit per second. So it is a rate of change. So it is a derivative, and it's a derivative with respect to time or with respect to t. And so we'll say dx over dt. The derivative of x with respect to t is equal to 1/2. We don't have to worry about units, at least not in this example. And then we want to know how fast y is changing. So dy over dt is how much? That's what we're asked. Okay, so here's what we do. We take our equation here and we differentiate each side with respect to t. Alright, well, I'm going to rewrite it first. So y equals x to the minus 1. We differentiate each side with respect to t. Well, think back to implicit differentiation where you differentiated with respect to x. Sometimes you differentiated functions of x with respect to x. Sometimes you differentiated functions of y with respect to x. When you differentiated a function of y with respect to x, you had to include a factor of dy over dx. But if you're differentiating a function of x with respect to x, you did not have to include such a thing. Well, here we're differentiating with respect to t. If you differentiate a function of t with respect to t, you don't have to include anything extra. But if you differentiate a function of y or a function of x with respect to t, then you need to include the appropriate factor. So let me show you that. So if we differentiate y, we're going to get 1. But y is this is not a function of t, so we need to include a dy dt. Now over here we differentiate and we get negative x to the minus 2, and again this isn't explicitly written as a function of t, so we need to include a dx dt. Alright, so dy over dt is equal to negative 1 over x squared dx dt. So we are given a value for dx dt. We were actually given a value for x too. We were asked how fast is y changing when x equals 10. So let's put all that in here. Negative 1 over 10 squared, and dx dt is 1/2, and so that looks like it's going to be negative 1 over 200. So that tells us that y is decreasing at the rate of decreasing. How do I know it's decreasing? Because that rate of change is negative. So y is decreasing at the rate of 1/200th of a unit per second. I hope that that sort of makes sense. That, remember, x is increasing, and as x is increasing, this graph is getting closer to the y-axis, and so we're above the y-axis, so y is actually decreasing. Not quickly, but it is decreasing. Alright, so let's do a better example that illustrates the types of problems you're going to see more closely. So in example 1, we are asked to suppose a square metal plate originally measuring 15 centimeters on each side is heated so that each side grows in length by 0.04 centimeters per minute. How fast is the area growing when each side measures 15.2 centimeters on each side? Well, in the previous problem, we were told that one quantity was changing at a particular rate, and we were told to find how fast another quantity was changing with respect to time. So what you need to do first is decide which are the quantities that are changing. Alright? So step number 1. Here's the method. Step number 1. Determine which quantities are changing with respect to time and assign them variable names. Then find an equation that relates the quantities. Alright, so in our particular example, we know that the length of a side is changing. So that's one of the quantities. And then we were also asked to find, so this side, each side grows in length by 0.04 centimeters. And then, so that's the quantity that's changing, and we know how fast it's changing. And then there's this other quantity, the area, and that's the quantity whose rate of change we're asked to find. Alright, so the two quantities we've got are the side length of a square, and I like the idea of calling that S, and then A is the area, and this is of the square, of course. Alright, so we need to come up with an equation that relates those two. Well, A is equal to S squared. Alright. Now, we're asked to find the rate at which the area is changing when the length of a side is 15. Do not substitute in 15 for S. Do not substitute a value in for a variable unless that variable always has that value. For instance, in this example, the side length is not always 15 centimeters or 15.2 centimeters or any other particular length. It's changing, so don't substitute in a value until after you differentiate. So that's what we need to do next, is differentiate each side with respect to t. Alright? So on the left side we'll get 1 dA dt. If you wrote that as just dA dt, I would not mind at all. And then s squared well, the derivative with respect to s is 2s, but we're trying to differentiate with respect to t, so we need to multiply by ds dt. Alright, so we need to go back over and find ds dt and s. My s looks a lot like a 5, so I think I'll use a cursive s. Alright, so let's see. Each side is growing at the rate of 0.04 centimeters. How fast is the area growing when each side measures 15.2 centimeters? This information up here about the square originally measuring 15 centimeters on each side, that's really irrelevant. It's a distraction. What we want to know is how fast the area is changing at the point where the square measures 15.2 centimeters on a side. So in this case, S is going to be 15.2 and ds dt is 0.04. And let's see, this is in centimeters and this is in centimeters per minute. Alright, so we can substitute in our values, and dA over dt is the unknown, but that's equal to 2 times 15.4 centimeters, or is it 15.2? Is 15.2. 15.2 centimeters times ds, which is 0.04 centimeters per minute. Now I'm going to just check to make sure I've got the values right. 0.04 and 15.2. Alright. So, all we have to do now is multiply and make sure we've got the right dimensions, the right units. So let's see. 2 times 15.2 would be 30.4, and then we need to multiply that by 0.04, and we've got centimeters times centimeters, that's square centimeters, and then that's over minutes. So the area is going to be growing a certain number of square centimeters per minute. I hope that makes sense to you, that we're talking about an area, and the area is going to be measured in square centimeters. Now we just need to multiply 30.4 by 0.04, and let's see, 304 and 4 is 16, 1, 12. I believe that's 1.216 square centimeters per minute. Notice that the rate at which the area is changing depends on two things. It depends on the rate at which the side length is changing, but it also depends on the length of the side. If we wait a little bit longer until the point where the side is longer, then this number will be different. I believe it will be larger.